You don't have to go, but that will be 10% off from your final grade, okay? Here. Project 2 is 10%. And we also have a lab tour on campus, April 25th. That is a 2 hours lab tour, and you have to show up, okay? For in-class student. If online students you want to come over, you're welcome. For those people cannot go to the field tour and the lab tour, you have to write 3 pages literature reviews for the field tour and 2 pages of lab reviews for the lab tour. Okay, that is 5 pages together, and no copy paste, no copy paste, no copy. Next Monday and next Monday is April 11th and April 18th. I invite 2 guest speakers for you guys, okay, 2 professors from nuclear department. You are required to show up. In-class students are required to show up for 2 guest speaker lectures. I will take attendance, okay. If you don't show up, I will give you maybe 20 or, let me see, 50 off from your project grade. About the field tour registration, I already sent out all the links to you guys. The password is 484. I received many email message asking me for the password. It's in the message, okay. And we still have, I just added 5 more spots for the UT campus tour, maintenance tour is April 18th from 2 p.m. April 18th is Monday, okay? Next Monday is the Oak Ridge National Laboratory Tour. We will meet in the lobby of the 2nd floor of this building. Okay, we have 3 cars to there. And then is April 18th is a UTK Maintenance Department tour. It's on campus, it's 2 hours. And you need to bring the hard hat, maybe glass, safe glass, and don't wear a slipper, okay? If you cannot find the hard hat, let me know. I can borrow one from you. April 20th is Innovate Manufacturing, is a plastic injection molding company, and we leave from UT. We leave at UT around 2:30 and arrive at there 3 p.m. Okay, 30 minutes drive. And April 21st is a Knoxville Locomotive Workshop Tour. Is a Thursday, okay, Thursday and 4:30. You guys need to do carpool by yourself. If you need you need a ride, let me know, and I will try to find a ride for you. Any questions for the tours? Yes.
What time is the lab tour?
Lab tour. 25th is just our class period. Yeah, start from 5 o'clock.
Do we just show up here at 5?
Yeah, stay here. We will split into 3 groups, I think. Do the rotation. One group in the class will give you some instruction, then move to the Perkins. On the Perkins B1 floor, we have the lab there, and do the rotation in this way. You have to write 1-page lab report, okay? You have to write 1-page report for the field tour and submit on the Blackboard, go grade. Last project 1, we found 3, let me see, exactly, 3 international students, no discrimination, okay? They copy the words by words from each other. Don't do that. You think we have around 120 students, we will not read your spot, you're wrong, we read your report, okay? Don't do cut, paste, or copy the words from others. That is not good. Oak Ridge National Lab Tour, we have to leave at 12 o'clock exactly. That means you need to be in the lobby 11:50 or 11:55. Okay, we cannot be late. Yes?
So we're going to do the leadership computing facility, right?
Or no?
Yes, I think Nick is sick today. He's the leader for that tour. And Phil will be there also.
I saw some notice for SNS. They were going to tour the accelerator as well?
Yes,
Cool.
SNS and HPC and maybe Atom Bomb Park or some I don't know, I forgot. Atom Bomb Archive. Yeah, maybe. I also told them to give you more introduction about the maintenance at HPC and SNS. Okay. Question?
What is to be on the paper?
What
do you want us to have in the paper itself? Like,
write your anything you want to write on your paper.
okay.
Except the complaints to me. Enough, too many complaints. Okay. Next Monday, and Phil will go over the solutions to the midterm, and that is our next Monday's job. You're good to go now. Finish the last part of digital signal processing. Last Monday, to give an introduction about the DSP part 1, okay, some basic principles. Signals, what is the digital signals, okay, and some basic statistics. Poisson distribution, the expected value for Poisson distribution is what? Is lambda, and the variance is also lambda, right? And how to use the Poisson distribution to calculate the probability for the no failure, last 2 failures. Normal distribution, what is the mean value for normal distribution is M, what is the variance, okay, and the normal distribution table, uniform distribution, okay, and the deterministic signal, then random signal, stationary random signal, independent random variables. How to acquire data, and sensors, and some basic terms, okay? What is the signal conditioning? Filter, low pass filter, high pass filter, band pass filter, and data assembly criterion. One is what is the aliasing problem? What is the Nyquist assembly criteria? How to calculate the sampling frequency? Time domain analysis for sensors data. Okay, we have the mean squared value, and the mean squared value is also the average energy of the signal. Mean square value is also the average energy of the signal, and what is the crest factor, what is the autocorrelation function, okay, all of them. RMS is the energy of the signal. Psi square is the energy of the signal. Use the psi square is the energy of the signal. RMS is the energy of the signal as well. And second moment is called variance. Third moment is called skewness. And if the right skew, the skewness should be positive or negative. Left skew is positive and negative. Kurtosis is a flat or a sharp peak, right? And then what is the crest factor? You use the peak value divided by RMS value. And what is the crest factor for sine wave? is a divided by square root of 2. If I give you this figure, how to calculate the crest factor, and what is the autocorrelation for one signal, I want to find the relationship between the signal at t and the signal at t plus tau, the interval, and how to calculate how to find the autocorrelation function for the sine wave, the autocorrelation function for the sine wave with is what? It's a cosine. It's a cosine. I remember it's cosine omega tau divided by t. It's a cosine omega tau divided by t. This is the autocorrelation function of the sine wave. And some properties for the autocorrelation. This is the autocorrelation function for temperature detector. This one is for the oscillatory feature. Okay. This is the cross relation function. We want to find the relationship. This time it's between two signals. Autocorrelation is just in one signal. These are two signals. We have a signal X and a signal Y, and I want to find the relationship between the signal X at time t and the signal Y at time t plus tau. What is the relationship between them? It's called a cross correlation. And how to calculate the cross correlation, and the applications of a cross correlation function is used to measure time delays in the fluid transport and find a causal relationship between two signals. And another word is called the cross correlation coefficient, and this is a correlation coefficient. Okay. And let me see here. Cross correlation is real, non-symmetric, and not necessarily reaches a maximum at tau equals to 0. And what about the autocorrelation? Is it symmetric or non-symmetric? Autocorrelation is symmetric, and will reach a maximum at t equal to 0. But cross correlation is non-symmetric and not necessarily reach a maximum at t equal to 0. Why? This is the cross correlation function. You will see this curve is non-symmetric, okay? And for the signal 2 at t, we notice equals to c times the signal 1 at t minus d. We find this relationship between them. And 1 tau equal to d, the cross correlation function reached the maximum y. See, if we let c equal to 1, and we calculate the cross correlation function between two signals, okay, this is the equation to calculate the cross correlation function, and we plug this t minus d into this equation, and you will have this value, have this relationship. And we know that the cross correlation function between the signal 1 and 2 is maximum 1, the t minus d equal to 0. Then tau equals to d. So that is why tau equals to d makes cross correlation function to reach the maximum. that's it. Finish. Actually, today I think it's more tough, but I make it easier. I prepare the slide by myself. Today we'll focus on the digital signal process transform is Fourier transform. Okay, so the goal of the digital signal process is to extract the information from a random signal. How to extract this signal from random signal? Okay, and we use a transforming in the DSP. We transform the signal from the maybe time domain or space domain to the frequency domain. Okay, and today in today's lecture we're going to cover how to transform the signal from a time domain to frequency domain, and what is the frequency spectrum, and what is the Fourier transformation, and what is the discrete Fourier transformation, DFT, and what is the fast Fourier transform is FFT. So when we have the signal, see, in the time domain, and we collect the signals, that will be a large data sample, right? And we want to compress this large data sample, and actually we can transform them to the frequency and to compress them. Especially for the rotating machines, the feature of the frequency will be more useful than the features in the time domain signal. And frequency spectral features can be used to quickly identify machinery degradation. And this analysis can be performed online. That is very important. This can be performed online. This is the example for a defect part of the bearing, and you will see a periodical signal in your data because of this defect. Okay. The period between these two signal between these two impacts is a period. So what is the first? My question is, what is the frequency? For a sine wave, if we let the amplitude is 1 and the period is also 1 second, it has a frequency of 1 cycle per period per second, CPS. Remember, the frequency is the how many cycles per period, and if we let the sine wave, the amplitude is 1 and the period is also 1, that is 1 cycle per second. So this 1 cycle per second is called hertz, or one cycles per period is called hertz. And also in our last lecture, we know the RMS of the sine wave is A divided by RMS sine wave is A amplitude divided by square root of 2, right? So this one is called the energy of the signal. For the frequency, when you check your electric apparatus, you will notice in the United States the frequency is always the 60 hertz, and the voltage is maybe 110 to 120. Then we also know one cycle corresponds to 360 degree or 2 pi radians, right? So we can use the radians. This is omega is a radians per second equals to 2 pi times the frequency. It's used to measure angular speed. My next question, what about how to convert rotation per minute to hertz? Now we have the rotation per second. How to convert the rotation per minute to hertz?
Multiply by 60.
Hmm?
Multiply by 60.
Yeah, something. Yeah. So this is not a rotation per minute. Actually, this is called the revolution. Revolutions per minute. What is the revolutions per minute? It's a measure of the frequency of rotation. Specifically. Number of rotations around a fixed axis in 1 minute. So this is the RPM. So 1 RPM equals to 1/60 hertz. And why?
What does it say, like, right above what is frequency?
Hmm?
What does it say right after the measure of the frequency of...
Rotation. Revolutions per minute is a measure of the frequency of rotation, specifically number of rotations around a fixed axis in 1 minute. And 1 RPM equals to 1/60 hertz. Why? Let me see. So we know that 1 hertz is a 1 cycle per second, right? If 1 hertz is 1 cycle per second, that means 1 hertz is a 2 pi radian per second. So we can get 1 radian per second equals to 1/2 pi cycle per second is hertz. Any question? Also, the 1 radian per second equals to 60 60 RPM, right? So 2 pi, so 1 over 2 pi hertz equals to 60 divided by 2 pi RPM. Then we have a 1 hertz is a 60 RPM. Then 1 RPM is 1 over 60 hertz. That is what. For this signal, what is the amplitude? What is the frequency? What is the amplitude, and what is the frequency? Yeah, the amplitude is 1, and the frequency is also 1. See, this is 1, and then the frequency is 1. From 0 to 1 is 1 cycle, okay? So the frequency is also 1. So what about we use the frequency as the x-axis and use the energy as the y-axis? We have the 1 frequency, right? We also have the, if the E square 2 is the energy of the sine wave. So we can express this signal in this way. Correct? So this is, we transform the signal from time domain to the frequency domain. See, this signal is a time domain, but this signal is a frequency. The frequency of the signal is 1. The energy is a squared divided by 2. If the A is 1, is 1 divided by 2. What if we have a signal with several frequency components? This is just one signal. Okay, one frequency. What if you have let me see, what if you have a signal in this way? The signal is a sine 2 pi t plus sine 4 pi t plus sine 10 pi t, 10 pi t. What are the frequency?
Back to 1 second.
By the way, why the sine 2 pi t plus sine 4 pi t plus sine 10 pi t, 10 pi t, it looks in this way. This is very important because it's the base of the Fourier analysis. Very, very important.
It's
You
like
just add the value
separate
together.
The same shape.
You can use any software. You can use any software. I'm going to use R. You can use MATLAB to add them together. The shape will look in this way. For example, let's see if I can do it. I wanted to simulate a signal. On the interval is -2.